Hi guys, this is Anmol Talwar and welcome back to another video with Talent Catalyst AI, where we strive to give you industry-specific artificial intelligence knowledge which will surely help you grow in your career ahead. With a work experience of over 7 years, I have handled projects related to natural language processing, artificial intelligence, machine learning, and generative AI across industries such as banking, pharmaceutical, financial, as well as marketing technology. So, let the learning begin. The topic for today's discussion is artificial neuron, which is a fundamental of any deep neural network. What we'll be going through is the architecture of that artificial neuron, and to understand the working of that artificial neuron, we'll be going through an advertising use case, right? And real-time industry use case on how a artificial neuron works. And the third thing is relating artificial neuron to a biological neuron. Biological neuron essentially are the neurons which are present in our brain. We'll try to understand how these two, artificial and biological neuron, are similar in terms of their working. So now let's try to comprehend the architecture of an artificial neuron. On the left side, this is the whole architecture of the artificial neuron, and over on the right side, we have the components in the artificial neural network, artificial neuron. So first one is our input. We have our input variables x1, x2, x3, and xn. For any problem statement to be solved, we need to have inputs. For instance, to understand these components better, let's have a problem statement wherein we need to have a probability, or we need to predict if if a student will pass the IIT entrance exam or not, right? For that to happen, we need some input features. For hypothetically, let's have three input features, that is x1, x2, and x3. The first x1 is, let's say, the IQ of that student. The second feature, let's say, the number of hours that student regularly on a daily basis study, number of hours that a student studies. And the third one, let's say, if the student studies in night or day. So this solves our purpose of the input variables, right? Those are the features used as the input to the neuron. Second is the weights. Each input is multiplied by the weights, which determines the significance, their significance. So for us to determine if the student will pass IIT or clear IIT, not every feature will have the same importance, right? Some features will be on a higher side to have a more predictable power as compared to the other features. So this is what weight does. Let's say in our particular use case, W1, that is the weight for the feature 1, that is IQ of that student, that, let's say, has the highest importance. Obviously, for a student to clear an competitive exam of this scale, the IQ must be very higher, and that will help them clear the exam better. So let's say W1, the weight for IQ is 200. Then now coming to the number of hours. Yes, number of hours is very important. The number of hours that student studies is very important, but as compared to IQ, that is a bit less. So we'll give this as 150. The weight associated with number of hours that a student studies is 150. Then the third feature, if the student studies in night or day or prefers to study in night or day, this feature essentially, according to me, that it's not of that high significance. So we'll give this W3, sorry, we'll have this W3 weight as 50. So this solves our purpose of weights. It essentially gives the significance of that particular input feature, how important that is, the predictability power of that particular feature to solve that problem. Then the third one essentially is the summation function. So you see, after having x1, that is our input features, and the weights, we have all of these things going into a summation function. Summation function essentially over here is a sum product function, wherein summation essentially is, if you see, x1 multiplied by w1, this is our multiplication, then added to x2, the second feature, and its weight, and then added to x3 and its weight. So this is a overall sum product of the features and their respective weights. This is what a summation function means. The next component is the bias. The bias is what we see over here. So along with the input features and the sum product of the input feature and the weight, we also have bias term that is going inside the summation function. So this means there'll also be a b over here. When we have the output of this summation function along with the sum product of the features and the weights, respective weights, we'll also have a bias term. Bias term essentially is the intercept term. So in linear regression, if you have remember the equation, it's m1 x1 plus m2 x2 plus there is an intercept c. So essentially, us in a similar way, here we have a bias term b that is introduced for the neuron to learn complex patterns and improve the flexibility of the model. It also acts as a switch to sway the model's result after to sway the models or the neurons result to a positive or a negative side. I'll explain this better once we have a understanding of what essentially is an activation function. So now let's try to understand the next component, that is an activation function. Activation function helps us introducing non-linearity into the neuron's output. So it is applied after the summation of all bias and the sum product of weights and the features. Introducing non-linearity helps the model learn more complex patterns that are implicit in that are embedded inside the data. So let's try to understand this with an example. What is non-linearity? Essentially, a major term what is trying to learn the non-linearity in data. So we have an example where we have IIT clearance predictability for the student, right? We have IQ, number of hours studied, and the third one is if the student prefers to study in day or night, right? If this were a linear equation, right? These are our features and this is the probability of the student cracking IIT. If this were the situation, this was the data, kind of these are the features scatter plot which help us understand the relation between the features, input features and the target variable, that is the probability in IIT. If this was the case, a simple linear line would have helped. But as the complexity in the features increase, we have this kind of data which is scattered. I am just showing you this in a 2D plane, but this is a n-dimensional plane. Specifically for us, it's a 3-dimensional plane because we have 3 features with us. If you see over here, if this is the kind of data distribution that we have for these 3 features, hours, night and day, introducing this particular linear line will not help solve our problem because it's not able to encompass everything. If we had a circular line like this, I have explained this in earlier videos as well, but if we had a circular line like this, which is essentially trying to get everything out of the data as much as possible, trying to get the trends, inherent trends of the data, trying to learn the patterns better because it's covering all the data. This is a non-linear trend or a non-linear, introducing non-linearity essentially into the data. This is what activation function does. Instead of just relying on simple linear trends, it will introduce non-linearity so that what happens is the neuron or the model will try to learn even more complex patterns. It will not only try to learn if a number of hours alone is interacting with the student's capability of competing in IIT or clearing the IIT, but it will also try to get patterns amongst number of hours and IQ. It will also try to get a number of hours compared with the night and day. Now these night and day will again have our links or the patterns to the IQ and so on. So we'll try to learn activation function better in my upcoming videos in depth, but now for this particular video, let's try to get a gist of what bias essentially is with respect to an activation function. Let's say the activation function we had over here is a step function, wherein if the threshold of the summation crosses a particular threshold, it will give the output, activation function will give the output as 1, and if not, it will give the output as 0. It's basically a firing function. If this threshold is breached, it will give the output as 1, else it will give the output as 0. Now let's say we have an example where the summation of the features multiplied by weights is 5, right? And the threshold over here is let's say 10. Now for the step function to fire to get the output as 1, we need an extra 5.1, right? This extra 5.1, if we add it to the sum product of features and the weight, that is 5 plus 5.1, it will become 10.1 and it will cross the 10 threshold, right? Remember what I told about bias? Bias is a triggering switch. It will help activate it will help the neuron to fire or non-fire based on in both the positive and the negative direction. If let's say the bias was 5.1, the neuron will fire. If the bias were around 4, we had said the sum of 5 and 4 will become 9 and the threshold won't be breached in this particular activation function, which will not fire. So the neuron will not fire in that particular case. So this is what we meant by a bias. It represents how easy it is for the neuron to activate as in 1, and non-activation means 0. If bias term is high, it will help the neuron to activate or fire regardless of the input. Understood? So this is done. The last part of the neuron architecture is the output, the final result produced by the neuron after the activation function. This is then passed to other neurons in the network for further processing. So we have the activation function. It will either be a 1, 0 or a probability depending on which type of activation function it is. If it's a threshold based, it will be 0, 1. If it's a sigmoid activation function, it will be a probability. Whatever it is, it will go to the output will now go to a similar neuron, a layer of neurons ahead of this. This is one neuron, which is essentially the smallest and the fundamental part of a deep learning neural network. There will be multiple neurons attached. Further, this output will go on to other neurons to have more deeper patterns extracted out of the data. Now coming to the use case, the advertising use case, which we talked about earlier. Let's say this is basically to understand the working of a neuron in depth. Let's say we have data for online ads and we have the input features, namely the type of ad, that is if the ad is the digital ad, is it a image or a textual ad, the same way you see in Instagram or Google ads. If it's a image ad, there's an image attached, or it's a plain textual ad. This is one of the features. The user age, the user who is seeing this ad, who you have projected that ad to, what is the age of that user, and what time of the day is the user seeing that ad. Of these features, our objective is to predict the probability of that particular user whom this ad is projected to, if the probability of that user clicking that ad, right? So in our case, we'll just, since we have three features, we have x1, x2, x3, which is being fed to a summation function, and then this summation function is being fed to an activation function, and then we have our final output. Apart from this, we have the weights, that is the significance of these features, x1, x2, x3, w1, w2, w3, and we have a bias term as well. So x1, x2, x3 are essentially ad type, 0 for image and 1 for text. X2 is our user age, normalized between 0 and 1. X3 is the time of day, normalized between 0 and 1. Let's say that ad type was image. So x1 essentially becomes 0 since it was an image. X2, the user age. Let's say the user age was 50 years and we have normalized the ages between 0 to 100, right? So 50 becomes 0.5 since it's a middle age. X3, the time of the day, since it's 6 a.m., it will become 0.25. 6 a.m. Why 0.25 is we have 24 hours and 6 hours have passed by. So it is a quarter. So hence 0.25. The importance, the weights or the significance that we have W1 as 0.8, W2 as 0.5, W3 as 0.3, saying that the type of the ad is most significant in predicting if the user will open the ad or not or click on the ad or not. The user age is second most important with the significance of 0.5, and then 0.3 is the last one, that is the time of the day. Now what we'll do is, and we have a bias function at hand. First, to get z is essentially till here, z, the output of the summation function. We have 0.8 into x1, x1 is 0, 0.5 into x2, x2 is 0.5, 0.3 into x3, x3 is 0.25, and minus 0.2. This is the bias term. We'll get a 0.125, right? Now this z essentially goes into an activation function. In our particular case, in this particular case, since we want the probability, we'll have a sigmoid activation function. We'll discuss these activation functions and the types of activation functions in detail in the later videos, but essentially sigmoid function gives us the probability. Any input to the sigmoid function, it will give you an output between 0 and 1, normalized between 0 and 1. That is essentially the probability of that particular use case. Okay. Now the formula for sigmoid is 1 divided by 1 plus exponential to the power of minus z. Z essentially is the output of that summation function, which we got it as 0.125. What we'll have is 1 divided by 1 plus e to the power of minus 1.125. This will essentially give you a probability of 0.648, or if we say it will be approximately 0.47, right? Now 0.47, if we have to give a threshold of 0.5, this will essentially say, this is essentially saying that the probability of user clicking the ad is less when the image, the ad type is image, and user age is 50 and the time of the day is in the morning, early morning, 6 a.m. The probability is around 0.47, which is not that much. The likelihood of that person clicking, the user of 50 years of age at 6 a.m. in the morning with the ad type of image, the probability is very low. So now let's try to comprehend what are the similarities between an artificial neuron, which we just saw all the components and the working, which is this one, and a biological neuron, which is there in our brain, which is a fundamental part of how our brain works, which is this one. Before going into the similarities between these two, I'll just walk you through how an artificial neuron was derived or how it was made. It was made to reflect a biological neuron. What happens is essentially, now think logically, when you were a child, you were just born, did you know the difference between anything that is wrong or right? No, right? This is all an activity of learning. You learnt during, if let's say your age currently is 25, you have learnt so many things from the age you were born, time you were born till the age that you are 25. You have learnt a lot of things, be it from your parents or be it from the environment. In the age from 0 to 25, there has always been a learning that was associated, and neuron was the one that was trying to learn and comprehend the differences between a wrong or a right based on the circumstances that you were there in, based on the teachings of your parents, based on the teaching of the environment. The brain learnt all those things. On a similar fashion, what scientists try to do is try to develop an artificial neuron which will also try to learn based on the historical experiences, right? But the only difference over here is a biological neuron, for us to learn all these things, it took 25 years and we're not still perfect, but same things an artificial neuron or a neural network can learn based on the discovery in just 90 days, because now GPT-4, which has an IQ of 155, close to 160, which is the IQ of Einstein, it was trained in just 90 days or 3 months. which is essentially better than most of the humans. So the advent of artificial neuron is based on a biological neuron. They both work on the same principles, on learning based on the circumstances or the data that is fed in. So going to the basic structure of a artificial neuron that we just saw, we have summing function, we have the activation function and the output. Similarly, we have the dendrites, which are the inputs to the biological neuron, similar to the inputs or the features that we have in our problem statement, right, in the artificial neuron. And we have the axon, which takes in all the input summation and everything, and it has also the activation function inside it. And then we have the axon terminals, which is the output, which will essentially, the output will be given to the next neuron for more complex problem data patterns to be extracted out from our sensory inputs, that are the dendrites. The information processing, as we discussed, is the same in both, wherein the artificial neuron gets the input, weighs the significance, sums it up, applies the activation function, and produces the output. The same way, a biological neuron receives the signal from dendrites, integrates them with the cell body, and produces the output. Coming to the learning process in an artificial neuron essentially is, it involves adjusting the weights of the connection between the neurons based on the errors. So one neuron will have weights, it will pass that output to the next neuron, then at the end it will compare it to the original target, it will modify the weights in the back propagation. This is how the learning in an artificial neural network takes place, right? And it's the similar in biological neuron. It can also modify the strength of the connections between them means multiple neurons based on factors which is known as synaptic plasticity. We need not go into the biological terms, but it's similar to what an artificial neuron can do, modify the weights. It can also modify the strength of the connections between the neurons. Now coming to the network connectivity, neurons are organized in layers and signals propagate from input to output through interconnected neurons. There are multiple neurons, as you would have seen in an artificial neural network, multiple neurons connected to form a whole feed-forward neural network. Similar way, in a biological neuron in our brain, complex networks of interconnected neurons organized in regions process different types of information, right? So in biological neuron also multiple layers of neurons are there which will help go through or identify certain type of problems in certain regions. The major part, that is non-linearity in artificial neural networks or the artificial neuron comes from activation function, which will help get the inherent patterns or the non-linear patterns. Similarly, our brain, obviously, because we try to club many things together and get an output based on multiple features, multiple circumstances, there is no right or wrong, because our brain processes things not in a linear fashion but in a non-linear fashion. Multiple things at a certain point for just single decision is what our brain tries to process. Essentially, that is how our brain also works in a non-linear fashion, similar to an artificial neuron, which uses an activation function for introducing non-linearity. Please do not forget to like the video and subscribe to the channel for more such informative videos related to artificial intelligence. Thank you.